So everything that Roger just went through gets at something fundamental, which is also tied to the question if we wish for the human species to be prolonged or to possibly go extinct. And one of the issues that came up when LaRouche had introduced the Strategic Defense Initiative and was taken up by Edward Teller on his own grounds as well, out in California back in the late 1970s and 1980s up to Reagan's announcement in March 23, 1983, was an issue of scientific method. If your mind is decrepit or has chimerical thoughts to it, attached to it, you can't make a discovery. And I think this gets at the heart of what made what's called the pinnacle of civilization, or the golden age of civilization, the 15th century Renaissance, a success, was that there was a renewed conception about the relationship of man, God, and its relationship to the universe. Now that in any way is not a religious question, it's scientific, and it's fundamental to understanding how do you actually affect states of changes in human society. We typically know the Renaissance in Italy as an artistic movement as such, and that is true. That is absolutely true. You know, we know it from the architecture, the various cathedrals that were built, the works of different artists like Botticelli. I mean, everybody knows Leonardo da Vinci in this case, but he's a prime example where, you know, if I ask people here, was Da Vinci an artist? The response is probably going to be, yes, he was. He drew great paintings. As a matter of fact, he drew very little paintings throughout the span of his life. Very little, and in ratio to ones that he did do, a lot of those were not even complete. So why does this man stand out as this great genius in human history? Well, you have to look at who he was in totality, and that was representing the essentials of what the Renaissance was actually about. It was a rebirth, as the word in French actually means, a rebirth of society. So that's particularly what I want to get into in concentrating on Kepler's work on the harmonies of the world. For those who are not familiar with, that was a contentious debate leading up to the announcement of the SDI all throughout California. I forget one of the guy's name, but one of the people associated with the Fusion Energy Foundation at the time, of scientific method. Is it okay to believe in the empty space, absolute time, one-to-one relations of space that Newton and his whole crowd were pushing? Or is it this harmonic relation, this overall organization of universal organization that Kepler actually had discovered and that was discussed very heavily from Gottfried Leibniz, who came about 100 years later. Actually, no, not too long after, a few decades afterwards. So that's what I want to concentrate on. It's going to be a little bit of a tricky thing to get into, but you know, things that don't come and stick, just go ahead and feel free to ask questions. But here's the first thing to really tackle at. To effectively go at what Kepler's discovery is about, we'd have to give up the notion that there's the existence of independent space and independent time. That is, that the way that we think when someone says, what's the universe, right? There's all these questions that we get thrown out to us, like how big is it? We don't know. When's the point where we stop discovering anything because we keep going out there, we figured everything out, and what else is there to learn? And there's an assumption there that you're not being conscious of, or that people aren't being conscious of, that ask that question. Is that they believe in absolute space, that space existed before anything else. And then God came by, walking by, and decided, hey, you know what? I think it's about time to start creating a solar system right here, and a galaxy, and all these other things that we're familiar with. And that's a false conception, is a fallacy of composition of how things are even created. Now, I want to play something I'm going to get into at the end, but it's going to be absolutely crucial to comprehend what I'm trying to get at. Because when you get at what's the concept of universality and the organization of coherent systems, and as far as we know today, they're solar systems and galaxies that exist within solar systems and composed of a coherent system of stars and probably other things that we're not entirely aware of, nebulas and things like that. It's much more related to how it's affected the classical artistic composers, Beethoven, Mozart, Bach especially, in particular. Bach's work, actually, from a lot of the work he did working with Buxtehude and other composers before him, before he got really famous and really impacted and took off with his music, they studied Kepler's work. They studied what he actually discovered is, well, what's actually going on within just the vicinity of our own solar system. That our own solar system can be understood to be organized around harmonic organizations or harmonic orientation. That has a deep association with music for the obvious. I mean, one of Kepler's key things in getting about to making knowable what he's trying to communicate to you, what he finds in the solar system, is taking how you respond to the audio domain. That is, there's a certain frequencies or sounds that you would listen to that you comprehend as, I like this sounds good. If someone plays something awful, you say, God, that guy should go back to school or just get another job. That differentiation is something that you receive and you perceive and you accept it as beautiful, as harmonic, or whatever word that you come up with, you know. That happens just as a central experience, but it also is knowable. And that's the key thing, is that the reason why you respond without any foreknowledge, right, any mathematics or any geometry applied to it, the reason why you respond to it is because they're accessible to the mind. Now, I mean, I'm not going to be able to get into that, but they're related to explicit proportions that you find from polygonal figures that you might have played around with at some point when you were young, like a cube, for example. You think of that. The square, right? The square is an equal division of a circle by 4 parts. You can have a proportion of 1 to 4, right? 4 representing the whole, 2 to 4, 3 to 4, etc., 4 to 4 being 1. Now those proportions are related, are intimately related to when you cut those and play them in a string. Those are the proportions that you accept as pleasant. You take the example of an equilateral triangle, right, which is the division of a circle by 3 equal parts. And what ratios are possible there? 1 to 3, 2 to 3, 3 to 3 being the whole. Those proportions are proportions that if you divide them and apply them to the division of a string as well, you will accept them as beautiful, harmonic, and any other positive attribute that you would offer. Now, taking that and transposing something that's knowable to you in terms of why you accept it as a beautiful concept or as a beautiful sound in this case, he then discovers, well, it's obvious that this is a harmonic orientation here, that you don't have these separate things, but the thing is that they all in unity can exist and create, though different distinct proportions, can create what you call a harmony or a coherent effect that you accept as something positive or something that sounds good. Can that represent a principle of orientation in the universe? In this case, his explicit vicinity or his laboratory is the solar system. Does the solar system in any way reflect these things? Getting away from chimerical thoughts, but getting explicit to the hard sciences, does it express these harmonic proportions that I know in thought represent something that's beautiful or received to the soul as a beautiful concept? And he does. Now, one thing I want to do is, as I mentioned, is I want to play something from Beethoven that I think would be useful as just a reference point to get into. Okay. And this is from his 57th sonata, piano sonata, if you guys are familiar with it. Is it on? Okay. No. listen to the rest later. Okay. Huh? It's called the Appassionata, Opus 57. Now, do I have any musicians in the house?
Yeah, it's in the key of F minor.
Yes.
F minor, it's the relative to A flat major.
Right. Now, do people understand what he means by that when he says it's an F minor key? Or what it means to be in any key? Because that'll be important into getting into what? Sure. Yeah. Right.
Beginning and an ending to the scale, and if you go around if you start out at one part of the scale, sometimes I guess you want to come around to the either beginning or an analogous the beginning of the scale to feel that something has been resolved. I mean, I'm not saying that's what it's all about.
Mm-hmm.
There's something to do with the resolution, tension between the notes, and then resolving the notes within that particular scale. And the scale, like B flat, won't be with a certain number of flats and sharps.
Mm-hmm.
As
Right.
opposed to C, which is all the way.
Right. Yeah, that's pretty good, actually.
C has no sharps or flats.
But what you said was key is that resolution,
It's all one.
right? Resolution. It means that we were somewhere, there's a development, there's a tension going, there's something that's engaging you. You're trying to find out what's that anticipation I got, and then you get to certain forms of resolution till you get to the end of the piece, so-called, the thing that bounds the whole idea. Now, it's important to then just look at, okay, well, we identified the scale, right? What makes up the scale? What makes up any scale? And you see that when you get the foundations of just that basic, even though you're not discussing music, but you just have the F minor scale, or any scale you can reference in your mind, you find that you have key elements within it that does exactly what you're asking for, to find the resolution, but to also create tension. Fundamentally, what you're doing is you're organizing a poetry. What you heard from Beethoven just now is a poetic idea. We tend to think that poetry is just words, but it's because we lose consciousness of, well, what's the poetry doing to the person? What's it doing to the mind? What's it doing to the audience? What effect does it have on you? How does it leave you? How do you think afterwards? And it's what makes these guys, genius in the work that they do, is they figured out how to do it in a principled manner where we call it music, but not at all separable from the concept of poetry. But just as in poetry, you're dealing with the language, you're dealing with your script, you're dealing with letters and words, but the words themselves don't organize the poetry. It's the thought of the person, right? It's the art of the person. And so here, what's our language that we're using, our script? It is the scale. Well, how is the scale formed, right? It was formed, right? It's not just, you can't just put any string and then, the piano just works great, right? It takes a skilled person to understand what that is. And that's where the importance of these proportions that I was getting at earlier are important, because they are the foundation that makes, I wouldn't say the poetry possible, but it's what's used in communicating his poetry. Beethoven is just one that I'm the most familiar with. I mean, other people probably have others that you have favorites, but that's my man. Now, then it becomes fascinating when you begin to see this reflected in the way our world is actually organized. Now, I do want to play around with one thing, just because you mentioned the scale, right? And we want to just go back to basics on that. Now, has anybody here, like I know I asked it, but do people here play instruments, like a string instrument?
Yeah, I play the violin.
Okay, that's a good. Has anybody here ever tried to play with an instrument before, just so I know where we're coming from?
Piano.
Piano?
But I play by ear. I don't read sheet music. I play it as I hear it.
Right. Okay, well, I'm going to play something in this thing we call a monochord. And if it doesn't sound great, feel free to buy us a violin next week. Or you bring his, yeah. He is. You should have brought it. Right. Okay, well, bear with me. I'm going to play something on this string, and then I'm going to just ask you very basic questions, okay? So here's the open string. Right? Did everybody recognize that?
Yeah.
You heard something that sounded like the scale?
Sound like it. Yeah.
Okay. Let me do it a different way.
La, T, go.
Was that anything?
That was the T, after you didn't finish it.
Why do you say that?
Because there should have been one more note after that one to resolve it.
Yes.
Or you skipped one.
He ended on go, but
Skipped one?
She's correct. She identified that what I just did was called bullshit. I faked it. But the previous one was not.
No.
Right? Okay. What I'm playing here is the same scale, but in a G key, sound of G. And G just simply meaning our beginning is how most musicians have identified it. Now that first one that you heard, that, just so I go through it systematically, right? We heard an open key, and then what you heard next was this string divided into 5/6. Right? Let me just draw that very quickly. Five, six, right, is from the hexagon. Then the next note that's the next part we played. What you heard there is this string cut into 3/4. 5/6? Oh yeah, I'm sorry. I should be very clear. What I mean by 5/6 is that out of the 6 equal parts that the hexagon makes.
I see. There is 6. Yes.
Yeah.
Yeah. Straight line.
This probably makes it a little confusing. Right. So out of all 6 parts, I played, right, 5 of it. But in a string.
You could have added one. You just don't add the last segment.
No.
You leave out.
Yeah. That 6th part, that one part of the 6, it's this part here. It's on the other side of where I'm playing it. So all you're hearing is 5 parts of 6. From here?
Beginning.
Oh, sorry. You want to hear the whole thing?
Full sound. And that's without any stop.
Right, and then?
I know what you mean by the
That's
other
okay.
side, though. How's that determined? I mean, could you just put 36 chords on the string?
Well, look at it this way. You see how I'm holding this down?
Yeah.
That keeps the
So-
wire on your left.
Right, I have this little thing here,
Holding's not vibrating.
and I'm separating the two sides. The side that I'm playing that you're hearing this part of the string being vibrated.
But there's more string that you're not using.
Right, which is this side here. Previously, what she was saying is I let it open, which means I did not separate any of it. You heard the whole thing. And now, I am applying in principle what you do there and saying if I were to divide the string into 6 equal parts, this signifies one of them, where this is 1, and this is 5. And I'm separating it by holding my finger down. You can use anything. And I'm playing that note. That's all it means. We can work on it a little bit more afterwards, so we can move on. I just want to get through this very quickly so we identify what we're doing. But there's the 5/6, 3/4, and I'll draw it up here. Right? There's that much of the polygon. Next was the 2/3, which is this sound, which comes from the triangle.
The last one has nothing to do with the one in front of it.
What's that?
In other words, the second string, John pulled string, you divided it into 3/4 instead of 5/6.
Right.
So it doesn't belong to the, didn't sound like it belonged to the first
Right.
string that you pulled.
Right. It's different.
So it didn't belong to that system.
They're different. They're different. They do. I'll just do it again, right? Systematically. Whole. 5/6. Oh, I'm sorry. Yeah, I know what you mean. 5/6 is a minor key. You are right. I meant to do 4/5, but right. You're right.
Okay,
You're right.
that's the second.
You're right.
That one is out of scale.
Right, exactly. Sorry, I just made a slight mistake. But that's the basic thing, is that you're hearing knowable proportions. And I'll call them out just by name. The whole, the first one that we identified, 3/4, 2/3, 3/5. This is not a harmonic, and then a half. So we see that as a foundation to what we use in the domain of music. My purpose is, can we see that in the domain of a planetary system? And the answer is, you can. And there's much more involved to it, which we're not going to get into in this session, but we can talk about it afterwards. The key one that I think people were curious about is when you had this sense of completion that you heard at the end, right? It was this note, which is half of the string. Yeah, it's exactly half. You notice that it has this quality to it as if they sound the same.
Yeah, but one fits with the other.
Right?
So not to be wrong.
Right. But what you said, right, it fits. There's something about it that like fits, but different pitch. And that becomes an essential quality to the importance of what's called there, what you heard was an octave, of these halves, where they play the same note but at different pitches. They fit like you were describing. And that is a crucial feature in music and instruments of your ability to play different voices, so-called, in a musical piece. As if the one that we just heard, you notice it was very low and it went very high. And what you're basically describing, you're illustrating that there's a knowability and something that's knowable to being able to move throughout a system, a musical system. Because there's always this conclusion that comes back. There's a boundedness to it, but not in the same way that you originally heard it. You can travel. So let's just keep that as an example, because I want to use one explicit thing, and I would need the projector at this point. To illustrate that. We're going to get right to it. We're just going to look at the solar system. As soon as I can find out. He's fine. Oh, yeah.
You're kind of saying, if you have an 8-foot long string divided up into certain lengths, and would that keep that pleasantness at those same spots? You know, if it's 8 foot, if it was 4 foot, you know, it was just proportional to its length. And if you made it 20% longer,
Mm-hmm.
you could chop it up the same way and would also have that pleasant points, sweet spots.
Exactly. And that's the issue that I was trying to poke at in the beginning of the absolute space and time, and the idea that magnitude and quantity defines everything, because what you'll begin to see is that more what defines truthful existence is ratios, is proportions, is relationships. Magnitudes don't matter like you just described. You know, this thing is probably about, I don't know, maybe 3 feet long and 8 feet long. You can still create that pleasantness that you're describing in an 8-foot string, so long as you maintain that relationship of a half and any of the other things. So magnitude doesn't really matter. What matters is the relationships. And when you get at what is a coherent system, that's what you're forced to acknowledge, is that you're dealing with relationships, a coherent system of ratios, and not absolute space and simple magnitudes in the way that's described typically. The question of how you keep evolving from that, that's a much broader topic that we're not getting into right now. But that's what Einstein was getting into and defining the universe as a space that's finite and unbounded. What's that?
If there were absolute space, then would the pleasantness come, let's say, if there were absolute space, would the pleasantness come from like equal, like 1, 6, 1, 6, 1, 6? Would that
Mm-hmm.
is that because the difference between the different notes is not equal? You see what I'm saying? There's different, like between 5/6 and 3/4 and 2/3, the absolute.
Mm-hmm.
They're different proportions.
Well, that's a problem, because the more that you try to really experiment to that, I mean, the bottom line is that there is no such thing as an absolute. So it becomes a chimerical question. It's the same thing as saying, you know, why did God decide to create the universe 5 seconds later than he could have? Like, why did he create it this time? Well, when you're dealing with two different states of space that are exactly the same, if that question is a valid question, to say why did God not create the universe an hour sooner as opposed to an hour later, then what you're saying is that there's a circumstance where God doesn't operate on sufficient reason, and therefore the creative human mind. That we can force ourselves into circumstances where we don't decide on reason, but on irrationality or arbitrary will. Arbitrary will is described by Nietzsche and all these philosophers at the Nazis. were really big and, big in supporting and supplanting the universities when Hitler took over. So, I mean, it's nothing wrong with asking this question, but we have to create a separation between things that are merely chimerical and questions that are actually guided by the principle of sufficient reason, which is the big topic and debate between Newton's whatever guy, Clark, I don't know what Clark was to Newton, and Leibniz was that exact question. And it comes up in the same way of space. Why didn't God create the universe that place? Like, why did he choose to do it here as opposed to do it there, right? 2 feet across. Well, that's true if absolute space is real, but when you're dealing with space being organized as a harmonic orientation, as a harmonic coherent system, space and time, you start to recognize only exist as a consequence of a harmonic intention and not independent from that. Let's just move on. It's not too much longer to this presentation. Now what I have here, can people see that? Probably small. Whoa, that is very small. Hey. Is it very blurry? Can people see that? Yeah, turn it off. And again, feel free to ask questions, anything that doesn't stick, because that's the way. This is not very easy material to dig into.
So when I see here, I see the sun, I see Mercury, Venus, Earth, Mars, Jupiter, and Saturn.
You're right.
And I see the parentheses, and I guess that's some kind of pitch.
Right. Now, what he's describing there, this is a diagram of this. Now, all those dots that are spinning around really quickly that most people can see, hopefully, right? Now, if I had a huge ladder that went out to infinity, and we went up to the top and you look down, this is probably what you would see. Probably not literally. But we're getting, yeah, exactly, a bird's-eye view of our solar system. Mercury, closest to the sun. Venus right here, our lovely Earth. Mars. Jupiter eventually is going to come. Oh, there it is. Right. Saturn doesn't fit. Didn't make the cut for this show. Just hold on, Eugene.
Aren't those concentric circles?
Yes.
I
No.
don't know what concentric means exactly.
Sort of. But then,
All coplanar.
excuse me?
Are all these orbits coplanar?
More or less, yeah. I mean, this is an illustration. There's more to it than what you're looking at here, but just to get right to it, no, the orbits don't circle the sun in a perfect circle. They orbit in ellipses, as I think, yeah, they're elliptical, as I think previous classes have described here in the last 2 years, as far as I understood. That becomes very crucial to this diagram that I showed you just a second ago. But I just wanted to make sure that we get an image that this is what we see happening. If the sun is a focal point in every single planet, for every single planet, meaning that in an ellipse, you don't have just one center, but you have 2 focal points that can help identify the parameters of the object. So what we're dealing with in actual physics is a case where the planets travel around the sun in a way where it's either closest to or furthest away to the sun. Interestingly enough, us being in the northern hemisphere, winter for us comes when we're actually at the furthest position of the sun. But that's because the Earth is tilted towards the sun. So you get an image of that. And then during the summer, we're actually the furthest away, from the sun. Now that becomes important to his thinking, to look for these harmonic proportions that we just identified in this scale, and that gave the ability for Beethoven to do what he did with this piece and many other pieces that other artists have done. The basic question is, how do I locate these harmonic ratios if they do exist? That is, that I begin to see a reflection of a reason, right, application to the creation of our world. What it boils down to is, well, first off, who's going to sense the harmonies? Without knowing it, we were the ones receiving the harmonies, the pleasure of the harmonies in the musical system, in really the audio domain. We were the receptors as well as the creators. You know, even though you weren't playing it, I was playing it, but I was receiving the same thing that you all were. In our solar system, what he identifies is what would have to be the receiver of the harmonies, which would also be the creator, so to speak, would be the motive power, the sun. And what he identifies is that this basic property, as I said, of extreme motions of the furthest position and the closest position to the sun, which also define the fastest motion and the slowest possible motion for any given planet, right? Which means that that is defining the property of any orbit. And everything else that occurs in between it is a consequence of achieving these extremes. So therefore, what he says, given that in the domain of music, we respond to harmonies much more perceptibly than we would in still figures, like the circles and other things that I didn't show you, but are possible in it, I'm going to look for harmonies in relation to motion as the sun would perceive them. And it would make the most sense that you would locate them where they are defined by their orbits, meaning the furthest position from the sun and the closest position from the sun, aphelion and perihelion, respectively. What you saw here that he identified was, he's right. The reason why I have 2 for each planet is to identify the longest position and its closest position to the sun. So that's true for Mercury. This is for Venus, right? Further away from the sun, obviously, closest. And as it goes up higher to Saturn. Now these numbers are really scary when you see them for the first time, because I don't know, you know, what in God's earth they are. But what they identify is, looking at how you see everything in common, what he looks at is at the extremities, but how much do they traverse in the span of a day? And it can be anything, but they have to be all uniform for every single planet so that the sun sees them all moving in a coherent way, just the way we're dealing with one system in a string. Now, I'll get to the easiest example that I think will help comprehend this, but what he locates is, you know, every single position. Now for Saturn, at its closest position to the sun, what he observes using data from Tycho Brahe, who was a contemporary of his until he died, but taking data and doing all sorts of, you know, all sorts of steps that is identified in the new astronomy, which, you know, I don't want to get into right now. But he locates precisely at what angular motion is traversed from the sun at these extreme positions in the span of the time of a day. Obviously, in this case, we're dealing with degrees, and so we're aware is, I don't know if people can see this, the 2 minutes 15, 2:15 here. You probably can't see that very well, but there's a little dash here. And there's 2 dashes here. That's important because what you're looking at here is you're looking at the fractions of a degree. And everyone can imagine what a degree is. It's very tiny. Of course, and the way that it works is that the further away you get, right, the wider it looks, but a degree is a degree. And, you know, if you're measuring a degree, say I'm the sun, and I'm looking at a degree of motion at that wall behind you, that's going to probably merit a size that big. But I decide to go about 4 miles, it might be that big. But the width doesn't matter as much as the angular motion that I'm seeing being traversed. So that's all what that represents. And this is in terms of a degree in fractions. So 2 minutes, there's 60 minutes in a degree, as well as there's 60 minutes and 60 seconds in a minute. So when I say minutes and seconds, I don't mean time. I mean the fraction of a degree. Is that clear?
And one question.
Sure.
That degree of transverse motion of the planet observed during aphelion and perihelion, during that one day, or let's say planet Saturn, the day that it has its aphelion,
Mm-hmm.
relative to Earth time, 24 hours a day on Earth.
Right.
Are you measuring with 24 hours a day on Earth, how many degrees or fractions of 1 degree or whatever?
Pretty much, you're just observing what actually happens. That's it. Like this is what happens. Just like if you go outside and you stand in the corner and the light turns green, the car's going to pass by, right? So you're standing there, you're looking at the sun, you're saying, what's going to happen in a day? This is what happens in a day. That's all it is. So what he observes, and we're going to just use this as one example, is at Saturn's closest position to the sun, what the sun sees Saturn do is move 2 minutes and 15 seconds of a degree in that position in the span of a day. Relating that to what its neighboring planet does, Jupiter, at its furthest position from the sun, what it does in a day is he records that it moves 4 minutes, 30 seconds of a day for the same amount of time. These two. That's what I'm looking at here. Now, does anybody know what the relationship of 4 minutes, 30 seconds to 2 minutes, 15 seconds is? Right. Can you let people know why it is a half?
It's division. 215 goes into 430 2 times.
Is that clear? Right? It's a half. So what Saturn and Jupiter do at these specific locations is generate an interval of a half, which is this feature here. Right? I don't know where I lost that thing. Can't find it. I'm blind. Well, oh, there it is. Right? What we were discussing before we got into this, if you were to ignore that. If you were to translate what Saturn and Jupiter do at these extreme positions, right, closest and furthest from the sun, into the audio world, you would be hearing this. Exactly.
The whole and the half.
Yes. Well, that's the relationship here. It's a half. And that's what you know what it is. Now, I can take another example they're more complicated, but that to me was the easiest case to comprehend. There's another one where if we were to take what Saturn does on its own, right? Saturn, we looked right now just at the relationship of Saturn and Jupiter, right? Clear? And it creates what we heard here and understood as an octave, which is what he identified as in any key resolves the key, resolves the music. But just taking another example, if you were to look at what Saturn does on its own, that is, what Saturn does in its extreme closest and its extreme furthest position, let's see if you can figure this one out. So its closest position is 2 minutes, 15 seconds. Its furthest position from the sun would see a motion of 1 minute, 46 seconds. of motion from the sun in the span of a day. Can anyone figure out what that would be?
Would it be like a quarter or
No.
less than a half?
Well, to get right to it, what he finds out is that 1 minute and 48 seconds, and mind you, we're talking about fractions of a degree, so a minute is a fraction of a degree, seconds is even a fraction of a degree, right? Really tiny. But he sees that the relationship of 2 minutes to 15 seconds to 1 minute, 48 seconds would create an interval of 4/5. What's observed is 1 minute and 46 seconds, and that's, the small discrepancy is not that important because it's really, 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 really tiny. I mean, 1 degree is small enough. So, in other words, what you see Saturn do in relationship to itself, between when it's furthest and closest away from the sun, is what you would hear in the domain of sound as this. Yeah. It's the first note of a scale that identifies it as a major scale. I'll play the whole thing. That's what Saturn does, and then to play the rest.
So while Kepler is observing this, he's putting it into some kind of musical perspective. And this is where you get, where Beethoven get his ideas and making his, well, using Beethoven as an example, that's where they get all this music from, by using the example of Kepler.
They do. They do, but in a sense of where is it going? Yeah. Because it's true. I mean, he's using sound to comprehend what one.
The universe is talking.
Yeah,
Speaking.
exactly. It's doing something.
Is that what they mean by music of the spheres?
Probably. I'm not too familiar with that, but I've heard of it. But in the way that what you're describing, I think you're actually right. But I just haven't looked into that specifically. But what you're describing is the way that if you were an archaeologist, right, and you heard of some possible civilization that it lived in a certain desert area that's been abandoned for millennia, how would you identify that there was an intelligent civilization there? You begin to find examples of pottery or something that reflects that they had a language, right? Letters, things that we would call letters in their case. In the case of yeah. Yeah. That's what we're finding here. Except that we didn't create this. But what we can say is this begins to reflect that rationality in the construction of the world out there is essential to the construction of that world out there. You begin to get a hint that it's not just random emptiness and some explosion just happened and things came together, but that this is a reflection of what's rational in your own mind. And you begin to get just the beginnings. I'd be very careful to say it's all absolute. Let's go outside and pat ourselves in the back and, I'll buy hoagies. But that we get the reflection that mind organizes the universe.
Well, maybe the universe is organizing our minds. I mean, this is shocking.
Big Bang and everything starts moving around and it's all organized? Wow. So what, is it gravity that caused this to happen? Gravity of the sun and gravity of all the bodies with each other?
I think that's what he's trying to develop, is get a concept of what is actually happening, and that things are organized with an intention, not at all random whatsoever. But it's opening the gateway to a different form of thinking that up to his time was not accepted. So it's shocking, but it's new. Prior to this, no one did this, which sounds really weird because all he's doing is just saying, oh, well, let me just see what the data shows, right? I mean, we're not even getting into questions of time and how they move. We're just saying, what do they actually just do? What would you record? And you begin to see that they reflect rational thought in the way that we know it in the audio domain as harmonic proportions. We use two examples, but if we had the ability to work through this whole thing, you would see that the whole of it orients itself in that way. You'll find the major sixth. You'll find the minor, right? You'll find other notes, things that correspond to notes in this scale that we just played, exactly, pretty precisely. And the ones that aren't precisely, there's a reason to it, which could only be understood in what the classical artists do with Bach and afterwards, which is, again, another topic of discussion. But as far as I know, we've run out of time. But I would love to talk about this outside, or take any other questions or thoughts that people have.
So Kepler grabbed this from the Danish astronomer Tycho Brahe, the one that got his moon kicked off.
Yeah, he used this
So
data.
he got, no, it happened in a battle. I mean, some kind of deal. But listen, but he grabbed the knowledge from him, and he put it to use and came up with this, right?
Mm-hmm.
So where did Tycho get his? Where did Tycho Brahe get his?
What Tycho Brahe did is he was very meticulous and very precise in measuring positions of stars and planets. He never really composed a meaning behind it. He just said, you know, where do I see Saturn in July 14th, 1501, for example, right? So he just recorded things that he saw. What Kepler did is he took that, used the method that he derived out of the new astronomy, right? By taking positions, taking angular positions, and then deriving distances, possible motions, deriving methods to discover motions of time and things like that. That's what he did with his work. So he used his precise data, which are precise in terms of measurements, where you actually see things. And the planet's a more sensitive issue because they move fairly regularly, right? And out of that, he used his method in the new astronomy to then begin to derive from his own discoveries, how do I know where they move? How do I know where they would be? And from that derived knowledge of how would they move in relation to the span of a day. So I can see if harmonic proportions do arise in the extreme positions of the planets. So it was a combination of the two.